Hi, everybody. In this video, we're going to talk about rational exponents. So these are exponents that are ratios or fractions. Okay. And actually, exponents that are fractions are directly related to roots. So that's kind of why all of this goes together if you're watching the previous videos here. So these are just another way to write roots. All right, so we have two different formats. I'll show you one first. And it basically says that if you have something that is a to the 1 over n, that is the same thing as having the nth root of that number. So what you're noticing here is, or hopefully you're noticing, is the denominator in the exponent is actually the same as the index of the root. If you have a negative exponent, don't forget that that negative exponent means that we're going to go ahead and just flip or use the reciprocal. So this is the same thing as 1 over a to the 1 over n, which is 1 over the nth root of a. Excuse me. And then if we need to, we could always rationalize that denominator if we wanted to keep simplifying as well. And remember here that a is not 0, okay? So just keep in mind in this case that a would not be 0. We don't want to ever divide by a 0. That would be undefined. So let's look at a few examples. So 64 to the 1/2. Let me see if I can brighten the screen a little bit here. That looks better. So again, that denominator there is going to tell you the kind of root you have. And this is a square root. So your index is a 2 here. But remember that we don't really need to write in square roots there. We don't have to write the 2 in, I mean. So it's just the square root of 64. And now this is something you can simplify. Square root of 64 is 8. Okay. 125 to the 1/3. So here I have a cubed root because that denominator is a 3. So I have a cubed root of 125. And now we know how to simplify this. The answer is going to be 5 because 5 cubed is 125. Right? 8 squared is 64. 5 cubed is 125. Okay. Now here you want to be a little bit careful. I do have a negative. The negative is not in the exponent though. So this is not a flipping or reciprocal problem. And notice that I don't have parentheses or anything. So actually the 1/4 only goes with the 16. And then that negative just sort of hangs out front like this. So I have a 4th root here. And again, that negative is out front. There's no parentheses, so that 1/4 is only touching the 16. The negative just comes over, gets attached, and then I have the 4th root of 16. So 4th root of 16 is 2. And again, that negative is sort of just kind of coming along for the ride here. Now that's different than this problem. Notice here I have parentheses. So that means this whole thing is part of the root. That negative is inside the root now. This is a 3, so I have a cubed root of -27. Now the answer there is -3 because -3 cubed is -27. Okay. Now in this case, we do have a negative in the exponent. So this is going to be this situation here. So if our negative is in the exponent, we are going to flip this. So I'm going to rewrite this as 1 over 64 to the 1/3. Once you flip it down, then that negative goes away. So it's a positive 1/3 now. So I'm looking at the cubed root of 64. And the cubed root of 64 is 4, so that actually simplifies completely. And that's because 4 cubed is 64. Now, there's nothing to do with the 1 there. The 1 is just a regular number 1. It's not in a root. So just keep that in mind. If you are using the reciprocal, if you're going from top to bottom, you can just put a 1 in the numerator. Okay. Now, sometimes we don't just have a rational exponent that has a 1 in the numerator. So what do we do then? So for instance, let's say we have a to the m over n. Well, what happens in this case is your denominator there is still going to end up working with the index of your root. Okay. And your numerator sort of works as a regular exponent. So this becomes the nth root of a to the m power, or we can write it as the nth root of a to the m power. It doesn't matter if you put the exponent on the inside or the exponent on the outside. So here the exponent is inside the root, here the exponent is outside the root. Both cases are actually good. So you usually do whatever more helpful. So for instance, if you know you can simplify that root, then usually put the exponent on the outside and we'll simplify the root first and then take the exponent. Other times it's more helpful to put the exponent on the inside. So you're going to have to kind of go back and forth to see what's most helpful for that particular problem. So let's look at some examples here. So I have 27 to the 2/3 power. Now remember the denominator is your root. So this is the same thing as the cubed root of 27 to the second power, or the cubed root of 27 to the second power. So your denominator is your root, and then your numerator is your power. These will actually give you the same answer. It just usually happens that one of them tends to be easier to simplify. And you want to look at both cases. For me, I know what the cube root of 27 is. The answer there is 3 because 3 cubed is 27. So I'm going to choose this version instead to use because I can simplify that root right away. So this becomes 3 squared, and 3 squared is 9. Now, if you did this version, it will probably work out for you, but it's going to be really hard because you have to do 27 squared first. That's going to be a really large number, and then try to find the cube root of that. So this way tends to be harder for this particular problem. So 9 to the 3/2. That denominator is your root. The numerator is your exponent. So here, if it's a square root, we don't have to write the 2 in. So it's the square root of 9 to the 3rd power, or the square root of 9 to the 3rd power. Okay. Again, usually one is going to be easier than the other if you can keep simplifying. Sometimes we can't, sometimes we can't really do much, but here we can. I know the square root of 9 is 3, right? Because 3 squared is 9. So I'm going to use this version, and then I'm going to find 3 cubed, and that's going to be 27. Okay, here I have 81 to the negative 3/4. So before I do any converting over, I do want to get rid of that negative exponent. So I'm going to flip it first to 1 over 81 to the 3/4 power, and then I'll make the change. So make sure you get rid of that negative first here. It's going to be easier for you. And then remember, my denominator is my root. So this is the 4th root of 81 to the 3rd power, or the 4th root of 81 to the 3rd power. Now, again, we can actually simplify this. The fourth root of 81 happens to again be 3. 3 is a popular number right now because 3 to the fourth is 81. So I'm going to use this version instead, and I get 1 over 3 cubed, which is 1 over 27. Now, there are some cases, excuse me, when this version is easier. So once in a while, you may come over a case where actually using the exponent first helps you to then simplify the root. So you kind of have to go back and forth and just see what makes more sense for that particular problem. So for me, I usually like to write out both versions and then look to see if I can simplify any more in either case. You don't have to do both, you just do one or the other, but you always want to simplify as much as you possibly can. Okay, let's do a few more examples. And this actually brings in the properties of exponents as well here, which we've learned. So I have 5x to the 1/2 multiplied by 7x to the 3/4. So think about this. So go back to your exponent properties, think about how do I multiply? Well, we have the same base, they're both x's. So what we do for multiplying here is our numbers multiply as usual. 5 times 7 is just 35. And when we're multiplying, what we do is we add our exponents. So it would be 1/2 plus 3/4, right? So think about a basic example. If I had 5x squared times 7x cubed, you would have 35x to the 5th. You would add the 2 x's here with the 3 x's here to get 5 altogether. So we can do the same process, but it's just a little bit harder because we're working with fractions. So I'm going to do some work off to the side. I'm just going to do 1/2 plus 3/4. You do need common denominators. So this first one I can multiply by 2 over 2. And I have 2/4 plus 3/4, which is 5/4. So this becomes 35x to the 5/4. Okay. And then in this case, we can go ahead and leave it. So sometimes they'll ask you to leave it in exponential notation like this. So we'll say, and here, if we left it in exponential notation, then we would be done. Or other times they may ask you to change it back to the root. So you could also go ahead and change this back to the root form or radical form, so root form. Let me do one of those as well. So let me just work with the x to the 5/4 for a second, because that's the only part that has the rational exponent. So if you wanted to go the other way, this is the 4th root of x to the 5th. And think about this. I have x to the 4th times x. So what I could do here is write this as x to the 4th times the 4th root of x. This is going to clear out, right? That assuming x is non-negative here. So if x is non-negative, then that 4 and that 4 are going to cancel. And you're left with x times the 4th root of x. So something like 35x to the 5/4 could also be written as 35x multiplied by the 4th root of x. Okay, so that would be the root form instead. Both forms are good. You're going to find that a lot of times when we're doing computations, we tend to like to keep the exponents because we know all those exponent rules already. We know how to work with exponents, so we will often use that form. But sometimes if we want a final answer, like in the last few examples when we were trying to simplify, then our roots are easier to work with. It's much easier for us to understand that as an answer. But these are sometimes easier for us to work with for operations. All right, let's try another one. So 32x to the 5/3. So 32x to the 5/3 over 16x to the 3/4. So your numbers out front are just going to work as usual. 32 divided by 16 is just 2. And then remember, for our exponents here, we subtract them when we're dividing. So it's x to the 5/3 minus 3/4. So for instance, if I had something like x to the 5th over x to the 3rd, this would be x to the 5 minus 3, which is x squared. That was the rule there that we've kind of learned before. So here I just have a little bit of work to do. I have 5/3 minus 3/4. I'm going to use 12 for my common denominator. So here I'm going to get 20 over 12 minus 9 over 12, which is going to give me what, 11 over 12. So I have 2x to the 11/12. And again, if we're leaving it in that exponential form, we would be done. Now this one here, if you wanted to write it as the root form, you'd have the 2. Your denominator is 12, so this is actually the 12th power of x to the 11. I actually can't simplify this because I would need at least 12 x's to cancel out the 12 here from the root. So I would just have to leave it like this. So again, a lot of times the exponential form looks a little bit nicer for our final answer. Okay. And let's do one more example here. For x to the 3/4 to the 2nd power. So remember here, when we have a power to a power, we're going to multiply these together. I do need to distribute that square to both parts. So this ends up being 4 squared times x to the 3/4 squared. 4 squared is 16, and then we multiply our exponents here. So I'm going to write that off to the side. So it's 3/4 multiplied by 2, which is 2 over 1. So this becomes 6/4. And then don't forget, you can simplify here a little bit. So I would have 3/2. So this becomes x to the 3/2. If we're leaving it in that exponential form, we would be done here. If we want to change it to the root form, let me work with this just for a second here. So it's a square root. So I have the square root of x cubed. Now this is a 2 and 3 is more than 2. So I can definitely split this. I could do x squared times x. That would give me 3 of them all together. Square root of x squared times the square root of x. And here, remember there's a 2. So again, assuming x is not negative, you're going to get that to cancel out. And then you would have x root x here. So another way to write the final answer, depending on which form you are in, is 16x root x. All right, so there's one more example I want to do that's a little bit different. And we're going to say simplify the 9th root of x to the 3rd power. So something like this is a little bit tougher. So whenever you're simplifying your root to get something to cancel, you need at least that much in the exponent, particularly if you have variables. That's the easiest way to do it. Here I don't have enough. I have a 3. But one thing we could do, another way to do this, is to change it over to the exponential form. So if I go backwards, my denominator would be 3 here, right? So that root is going to be your denominator. And then that 3 is going to be my power. So it's 3 over 9. And now you guys know how to work with a fraction. We can divide these both by 3. And we have x to the 1/3. So if I wanted the exponential form, I could write it like this. Or if I want the root form, this is the cubed root of x to the 1st power, right? Because my numerator is 1, but we don't write that in. So it's just the cubed root of x. So we can go back and forth between the two forms and help us simplify. So it's good to know both ways, because sometimes it's easier to simplify as a rational, and other times it's easier to simplify as a root. So it just really depends on the problem. One last thing I want to note here is that your calculator can typically compute rational exponents. Just make sure you use parentheses when you input that exponent. So for example, let's do the cube root of 125. So let's say I asked you to find the cube root of 125, and maybe you're having a really hard time. You're not as good with your cube or 4th or 5th roots and so on. How can you find this out using your calculator to help you without just doing trial and error? Well, you can change this over to the exponential form. So if there's no power written in, there's a 1. So this is the same thing as the cube root of 125 to the first power. So I can write this as 125 to the 1/3. 3 is for the denominator here for the index, and then there's no power, so it would just be a 1 for your fraction. And then let me show you my calculator. So I have the TI-83 graphing app, but actually most calculators probably have an exponent feature on them, and I could probably still do this. So here I just type in the 125, and then I use my exponent key. And then the only thing I'm going to do is I'm going to put that 1/3 in parentheses. So 1 divided by 3, and I hit enter, and I get the answer of 5. So it's just a nice way where if your calculator doesn't do other roots and you're kind of stuck, you can use the exponential form here. Let's do another one that we did before. So let me do, what if you had 9 to the 3/2, right? You can do something like that on your calculator too. I just hit 9, raise the exponent, put my exponent in parentheses, and then you'll get the answer of 27, which we did by hand. So it's just a nice way to check your work here. And again, most calculators that have an exponent key can handle this. You just use parentheses around that exponent. I want to show you as well on just a regular calculator. So this is the calculator app that came with my iPhone. I know you may not have an iPhone, but hopefully you have a similar calculator anyway. For this one, if you turn it on its side, you will see an expanded calculator open up. And this is a little harder to work with, but you can still do it. So I'm going to do this bottom example here, this 9 to the 3/2 equals 27. So what we do is we type the 9 first. Then this x to the y is your just general exponent key. You hit that, and then here are your parentheses. So I do parenthesis, 3 divided by 2, close parenthesis, and you'll see that's the calculation for 3/2. And then you're going to hit equals again, and you'll get the 9 to the 1.5 power. So that's another way you can do it, okay? So if I do this one, I can do 125 exponent, parentheses, 1 divided by 3, close parentheses, equals, and there's that 5 that we did for the other example. So if you don't have a fancy calculator, you probably still have a way to do it on your calculator. You may have to play around a little bit with the functions to see the order put them in, but as long as you have parentheses and an exponent key, you should be able to get those rational exponents to work. So it's just a really nice, I think, tool to have, not only to check your work, but sometimes some of them can be pretty hard, particularly if you have really large numbers. So it's nice to be able to have a calculator that can help you solve those answers or those problems, I guess.